So hi everyone, I am Rushan from Georgia Institute of Technology, working with Qi. I am here to talk about our latest work on structure preserving transfer of Grad-Shafranov Equilibria to MHD solvers. So our work here is based on our work presented last year at MFEM workshop by Qi, which is a GS solver for axisymmetric equilibrium. So first of all, I will talk a little bit about the GS solution. So GS solution is derived from MHD equations. It is MHD equation with an extra assumption, an actual symmetry assumption. So because in a tokamak, the field is axisymmetric, we can represent our magnetic field with a psi function and an f function here, corresponding to the poloidal and toroidal directions. So with this assumption, with the order MHD equations, we can derive the GS equations here, which results in our governing equations here. So the task of our project now is that we want to transfer our GS equilibria to MHD solvers. So when we're doing a MHD simulation, we usually will start from a equilibrium, and this equilibrium is usually obtained from a GS solver. However, although we use psi and f to simplify the solution of equilibria, when we are actually doing MHD simulations, we actually need the magnetic field directly. So, so consider these two equations that I talked about just now. So we can derive the poloidal and the toroidal directions of the magnetic fields and the current density fields like this. So the goal of our project is that we want to investigate the error during the transfer process, because like usually in current implementations, this transfer process will result in loss of error, and this error is very important because usually when we do MHD simulations, we are doing stability analysis. So when we do stability analysis, we apply a very small perturbation and see how the field will evolve. So this small error introduced during this transfer process will influence our stability analysis a lot. So in this project, we are going to look into three error sources. The first source is that we want to see whether there is incompatibilities between the GS and MHD finite element spaces. The second source is that oftentimes when people do this transfer process in current implementations, the GS and the MHD meshes are not aligned, and we're thinking that perhaps this misalignment will result in loss of error. The third source is we want to see whether the discontinuities at the separatrix will result in a large error. So before we dive into the our experiment setup, there's one thing that I have to bring about is that in compatible finite element, there is a natural FEM spaces that correspond to each differentiation operation. However, we cannot really follow this natural finite element spaces in our experiment, because usually when we are solving the GS solutions, the psi and f are both in CG fields, and if we do follow the natural FEM spaces, we will result in toroidal direction in CG and poloidal direction in HDIF. And however, this does not these are not consistent with each other, because when we are because if we have HD for poloidal direction, we will need the toroidal direction in DG instead of CG, as shown in the graph here. So therefore, for our setup experiment with the compatible finite element, we will introduce one step of a natural projection step here or here. Like these two are both steps that are unnatural in terms of the compatible finite element. And besides the compatible finite element spaces, we also experiment on the vector CG field, which is usually used in current implementations. The second source I've discussed is that the misalignment between the GS and MHD meshes might lead to loss of error. So in our experiment, we'll just show a result with a very small perturbation. We'll see that whether this small perturbation will already result in loss of error, so that if it is misaligned, it will definitely lead to a very large error. So we use a very small amplitude of 0.05 to see this result. And the third one is the discontinuity at the separators. In order to test it out, we conduct a refinement along the separators. And at the same time, we also test out, like, instead of just doing refinement, we do refinement with an alignment with the mesh and between the mesh and the separators. We'll see whether this further alignment will result in less error. So our experiments are based on the Taylor state equilibrium that is obtained from our previous work on GS solvers. So here are the results. So the first one is the experiment on different projection paths. We show here that in terms of the force balancing, it is very significant that the first projection path resulting a much smaller error than the other two, especially the one that we usually use with vector CG. However, this doesn't mean that the first one is always preferred, because sometimes we may also care about the divergence-free properties of the magnetic field. So in terms of the divergence-free property, it turns out that the second projection path actually results in smaller error. And then now is the result experiment with the mesh misalignment. So I've just mentioned that this perturbation is very small, but with this very small perturbation, there's already a lot of errors that is introduced in the force balancing. And in terms of the discontinuity at the separators, we find that a refinement is very important. It results in much smaller error along the separators, but it seems that with the further alignment with the separators, it doesn't really result in smaller error. So our conclusion is that the choice of finite element spaces and the mesh alignment does matter a lot if we want to obtain a very small error. So if force balancing is more important to you, then you should choose the first projection path here. But if divergence-free property is more of your concern, you should choose the second path. But it turns out that the vector CG path doesn't perform well for both cases. And mesh refinement near the separators is very important, but the alignment with the separator is less so. So for our future work, we will try to do a team up to automatically align the mesh with the separators during the GS solution, which can be important for transient MHD simulations, such as this anisotropic diffusion. So this graph here shows, like, I just did a manual alignment with Gmesh, but we will try to adopt a team up in our workflow. Thank you.
All right. Thank you guys for having me. I'm very happy to be here presenting my work, developing this framework for multiphysics biomedical modeling using domain decomposition with a keen focus on a specific application, which is cardiac radiofrequency ablation. This is a brief outline. Essentially, I'm going to present some clinical background, go into the details of the multiphysics and domain decomposition model, and then present some preliminary results of our project. This is a clinical application, so let me start with a very brief clinical background. So we can essentially define an arrhythmia as any sort of irregularity or problem that in a person's normal heartbeat. And cardiac ablation is a minimally invasive treatment aimed at destroying the target area that is causing the abnormal electrical behavior by delivering some form of energy in the form of heat or cold. And among different treatments, cardiac radiofrequency ablation is the gold standard among them. Now, if this is the gold standard, why essentially do we need modeling? Well, because despite being the gold standard, it's still not fully predictable. And there is a large amount of patients that require reintervention after the first treatment. So having a reliable virtual tool for cardiac ablation can definitely help in different directions, as you see here. But let's dig deep in the multiphysics model for now. So if you recall what I said about the treatment itself, so you understand that we need an energy source. So in this case, it's radiofrequency. It's a hyperthermic treatment. So the tissue is gonna heat up as a consequence, and we're gonna model the heat transfer. We know that the tissue is gonna be destroyed. So we want to some extent, account and explicitly model this cellular dynamics. And it's gonna be an intracardial ablation. So essentially, we're gonna have blood flowing, and we want to account for that too. This is a proof of concept of our framework. So we wanted to stick with a geometry that was simple enough to have more control over, but still like resembling our application. So we have a slab of tissue, cylindrical electrode, and surrounded by a fluid domain. For the first block, we have the radiofrequency source. Within the spectrum of radiofrequency, the tissue is almost completely resistive. So this boils down to compute essentially a Poisson equation for the fluid and for the tissue. We discretize in space with Q4 elements, and we solve the linear system with CG precondition with the lower the refined version of AMG. For the heat transfer, in the electrode, we have a plane heat equation. We have a convection term in the fluid. And for the tissue, we essentially have what we call the pan-bio heat equation, which is a standard heat equation augmented with some volumetric heat generation terms, specifically a metabolic perfusion term. And the most important is the Joule heating term due to the radiofrequency treatment. We discretize in space with Q2 elements. In time, for the time discretization, we use an S-Dirk 2-free scheme, and we solve the linear system arising from the use of the implicit scheme with a GMRS precondition with a matrix-free Jacobi smoother. The cardiac tissue is known to be anisotropic due to the inner fiber microstructure. So we account for this in the tissue model by using a electrical and thermal conductivity tensor, which are tensor, and they are defined based on the fiber direction, which rotates intramurally. For the cellular depth, we use a continuum approach. So in each point, we assume that the tissue can be in different states described by fractions, can be alive, dead, or vulnerable. So it's sort of an intermediate state, a recoverable state. And the transitions are determined by a system of free couple ODEs where the kinetic coefficients are temperature dependent. We solve it with the eigenvalue method due to the simple nature of the system. So essentially, we pre-compute the symbolic form of our eigenpairs, and given the specific value at a specific point of the temperature, we evaluate them and use that to advance in time. Last but not least, we have the fluid dynamics solver. So the blood is considered as an incompressible Newtonian fluid, so we're solving the incompressible Navier-Stokes equation. The solver that we use is essentially an MFEM updated version of an old solver from our group, this Aladdin solver. We use a same implicit convection term. For the time discretization, we have BDF up to order 3. For spatial, we have the stable Taylor-Hood elements Q2, Q1. We have time adaptivity, as I will explain in the next slide. And after discretization, we end up with the usual settle point system, which we solve with a flexible GMRS preconditioner with a specific block preconditioner, which arises from the algebraic splitting theory. So it can be seen as an inexact value factorization. As the factorization method, we use this high order Yosida, which is momentum preserving, and essentially the pressure correction step occurs in different intermediate steps, depending on the order of the pressure correction. And this gives us more accurate pressure correction, and also as a byproduct, a pressure correction based error estimator for time adaptivity. So far we have described what happens in each block and how each physics is solved, but we haven't described how we intend on coupling the different domains, and we do it with domain decomposition. Particularly, this is based on a two-level segregation approach. The first one is the multiphysics segregation. Essentially, we solve the different physics in a staggered fashion within each time step. And specifically for the cell depth and heat transfer block, we resort to a strong splitting to increase the accuracy of that specific sub-block. Then we operate a substructuring by subdomains, meaning that we do a non-overlapping domain decomposition based on the physical domains that we have in our geometry. And for the transmission condition, we implemented both a Dirichlet-Neumann and a Robin-Robin coupling, and the latter one has been tested mainly on the radiofrequency part. For the results, we again, this is a proof of concept, so we spent some time verifying each solver, then tested the domain decomposition, and finally the radiofrequency ablation. And for the verification, we follow standard approach, so manufacturer solution. We tested the convergence rates plus some additional toy problems for both the heat transfer, radiofrequency, and Navier-Stokes. For the domain decomposition, we first verified that the Dirichlet-Neumann within a single subiteration followed linear convergence of the error for both the heat transfer and radiofrequency. And then we performed an H refinement and P refinement study. For the H refinement, we assumed the polynomial orders described for the previous models, and we progressively refined the mesh, and we showed that essentially the scheme is mesh independent. For the P refinement, we kept the mesh the same, but we increased the polynomial orders, and we found like a slight increase in the number of iterations to convergence, but still in the same ballpark. We also tested the anisotropy both in the tissue-only case and in the free domains coupled problem. And then last but not least, we have the full simulation of including domain decomposition on the free problems, on the free domains. Now, to wrap up, we developed this model, this multiphysics model for cardiac radiofrequency ablation, which uses domain decomposition, but we were also thinking, can this be used only for this specific application, or does it have potential for being extended to other application? Well, it does, luckily. So if you think about the energy source, if you replace that and the coupling term in the heat transfer equation, you can solve other types of ablation like microwave, ultrasound, laser. You modify the property of the tissue, you can solve other type of ablation on other tissues, but you can also solve problems that look different but are conceptually the same. This is also a problem from our group on erosion of bioresorbable stents. It looks different, but conceptually it's the same because you have three domains, the lumen, the wall, and the strut. In the lumen, you solve Navier-Stokes, and in each domain, you solve essentially an advection diffusion reaction equation similar to our heat transfer one, coupled with domain decomposition. Just to conclude, some future plan, where can we go? Essentially, from the multiphysics perspective, we can expand and improve the models from different aspects for fluid dynamics, for the heat transfer, for the mechanics. We want to develop some old work we had on the thermomechanical response of the tissue and eventually develop also the electro-tissue contact model. For improving the computational efficiency of the model, we can go in two different ways depending on what is the final goal. Essentially, if one wants to perform high-fidelity simulations, for example, if we want to investigate and unveil essentially the unknown behind the lesion formation in cardiac radiofrequency ablation, one way to go is to extend PA and GPU acceleration to all the solvers to scale the simulation to like larger scales. But one thing we are investigating, if you want to do a clinically suitable simulation where you're bounded by computational power available and time, is to use for each sub-physics block, reduce order modeling to accelerate the simulation, with the ultimate goal of essentially doing surgical planning and therapy optimization with this model, in which case we would need to identify the optimality criteria, use ROM techniques to accelerate, and then eventually also do XV when preclinical validations. And with this, I thank you, and I'm open for questions.
Hi, everyone. I'm Vimarsh. As you can see here, I'm a fourth-year PhD student at UIUC, and this work was kind of done with folks from UIUC and Argonne National Labs. We also have a bunch of collaborators, without which this work wouldn't have been possible. The outline for today's talk is I'll be talking about compiler-based differentiation. Then I'll give an introduction into what enzyme MLIR is. Then I'll talk about like how you can like use talk about case studies like you can use tensor algebra optimization and higher order derivatives in combination with enzyme MLIR. Finally, I will talk about AD specific optimizations that you can do in enzyme MLIR itself. To start with, derivatives are kind of key to science and ML. In scientific computing, you kind of use them in uncertainty quantification or differential equations. In machine learning, obviously, it's being used heavily in backpropagation and training. This is kind of like a cool animation from EnzymeCon 2023, which shows like a differentiable molecular simulation, again, by one of our collaborators who used Enzyme. To start with, even if you don't know what automatic differentiation is, at its core, you can think of it as like this. You have a primal function, for example, the ReLU function here. You pass it through your automatic differentiation tool to get a gradient function. You generate this function ahead of time before getting any inputs. When you compare this to like a standard approach like finite differences to compute a gradient, in finite differences, you usually your gradient kind of depends on how well you choose your epsilon value or the perturbation. If you choose it to be too big, you get a false gradient. If you choose it to be too small, you can run into like cancellation errors here. But with AD, you don't have this issue because you have already generated the code for the gradient. So it's just a question of like, you always get the exact answer. If you compare existing automatic differentiation pipelines, they usually take in code written in like a specific language. It can be C++, Rust, or Julia. You generate the derivative code in the same language, and what this AD tool will do is that it will kind of handle all of the language-specific idiosyncrasies that you have before lowering it to like a general IR like LVM and giving you the executables that you want. With a compiler-based approach, instead of like writing a specific AD engine for every language out there, you first lower your code to LLVM IR, and then you do differentiation on that LLVM IR that you get. This is better because one, now you don't have to do the re-implementation effort for every language out there. And two, you can also run optimizations which are already in the compiler before even going ahead and differentiating the code that you want. That was like a very quick TLDR of what Enzyme does. We'll now talk about what MLIR itself is. MLIR, you can think of MLIR as this new compiler IR where you as the user can define your own dialects or instructions, optimizations, or analysis. There are quite a few common MLIR dialects out there. For example, you have the arith dialect for arithmetic ops, or you have a linear dialect for linear algebra operations. You can also represent control flow using SCF. In our case, we represent automatic differentiation using the enzyme MLIR dialect here. The core idea with MLIR is that you can mix and match operations across multiple dialects, or in the traditional sense, IRs. And this is kind of unprecedented if you think about it. Like, if we look at this example here, this set function kind of defines a function where you're kind of like setting the elements of this array ARR to val. I hope my cursor is visible. Great. You kind of define this function using the func dialect, and then you define a for loop using the SCF dialect, wherein which you use this memref.store op from the memref dialect to store the value into the array. Finally, you use the arith dialect to kind of like square the value and return it. So the enzyme dialect kind of looks similar in the sense like you have this function set here. You have this enzyme.autodiff operation, which kind of takes in this function that you defined right now, takes in like a couple of inputs, which this derivative function needs, returns the outputs. You also seed it with like certain activity values, which I'll get to later towards the end. But that's a very quick introduction to an MLIR and enzyme MLIR. The question you might ask is, why do we need enzyme MLIR when you could also consider MLIR as a front end? You could lower it to LLVM and just be happy with the traditional enzyme approach, right? You still get like LLVM's compiler optimizations already baked into enzyme. The difference here is in MLIR, because you as the user define your dialect and optimizations, you want to be able to run those optimizations on the derivative code too, or before generating the derivative code. So to kind of like capture that optimization angle, we have enzyme MLIR. We kind of designed that. And with this, now, because we have a first-class MLIR dialect for representing AD in MLIR, we can like kind of coordinate between AD and optimization together. So this is like a case study of tensor algebra optimization with enzyme MLIR. Stable HLO is an MLIR dialect for tensor algebra operations. It's kind of like developed by Google. A few of our collaborators in our CGO 2025 paper kind of implemented 200 plus tensor rewrite rules to just optimize tensor code. How this helps us is that our hypothesis here is that on the primal code, if we run these optimizations before generating the derivative, it will lead to outsize impact for derivatives. And just to get an idea as to how these rewrite rules kind of look like, they're really simple. I mean, like you have a tensor x, you add 0 to it, you get back x. Or you take a transpose of a tensor, it's the tensor itself. Imagine an operation where you have like really large tensors, and you're kind of like operating on those tensors, but at the end, you're taking like a dot product with like a slice of just 10 elements, right? You could, and this is what the a tensor rewrite rule does, is that you could like kind of like push these slices up using this push slice up rule. This kind of reduces the size of your matrix multiplication to kind of like just work with smaller intermediate values. Yeah. We did this for a CAN network in Julia, and we got a 2x speed up on the primal, but we got like a 14x speed up on the back propagation code. Since we are running low on time, I'll skip the higher order AD case, and I will move directly to what we are doing. The idea with activities is in Enzyme, you kind of attach this activity attribute to every input and return argument that you have. And what the autodiff operation does is that it takes this activity and it kind of determines how to generate the gradient code based on that. For example, everything is active here, so our generated code will compute both the primals and the derivatives. The idea here is you can use other compiler information like use definfo to kind of optimize this activity before even generating the code. And to just work you through an example, it would be like you have this function square. It computes the square of its arguments and returns it. You have the derivative for that here. But it turns out you're only using like 2 of those outputs. You're not using all of those outputs. So the first thing we can do is we notice that we are never calculating the gradient of y. We just eliminate it using like this constant activity here. I mean, like you can look at the table and you'll realize that we are just not differentiating in this case. And remember, we are doing this before even generating the gradient code. You could also, I mean, this is just an example to see like, hey, you're not computing dy anymore. You could also do like another no-need optimization where we realize we are actually computing the initial output, which is x squared in this case, but we don't really need to return it. So we can just say an active no-need, and this in turn, once the code is generated, will trigger dead code eliminations. So this is like a pretty quick summary of the activity optimizations that I'm implementing. There are more that I'm implementing, like how do you like batch across multiple invocations to like an autodiff call. For example, one of your primal functions can have like a fib of 100 call or something like that. And by batching across multiple invocations of the authoritative call, you could like kind of save on that. Again, to give a quick summary, I first introduced the enzyme approach, told you about the enzyme MLIR dialect. We saw like a simple tensor optimization example. We skipped over higher order derivatives, which is fine. And then we talked about return activity canonicalizations. But yeah, that's it. Yeah. Yeah. Yeah.
Cool. Thanks, Vimarsh. Okay, we can now have questions for Rushan, Leonardo, and Vimarsh. I can start with a question for Rushan. You mentioned you want to align your mesh with the separatrix. In your case, how is that represented? Is that like a level set, or how you? What's your input for aligning the mesh to it? Oh yeah.
Yeah. Basically, we use the line that like it corresponds to psi equals some constant value. Yeah.
Okay. So it
So
is a discrete function, like an isosurface.
yes.
Okay. Any other questions?
I have a question for Vimarsh. Who is producing the MLIR that the enzyme MLIR is working on? What's the idea?
So it depends on the language, but for C++, there is an enzyme MLIR frontend called Polygeist. For Julia, there's another MLIR frontend called Reactant, which works through tracing. But ideally, there are frameworks out there which expose, which like convert your code to like MLIR, and then you can run the optimizations that you want in MLIR.
Yes. So yeah, that's my question. Is there some other tool that you're still writing in high-level language, or do you expect this community to write MLIR,
No.
which will be an ask? Okay.
Okay. Any other questions? If not, think we can.
I just have a comment. I couldn't formulate the question because Leonardo presented so many cool things that I just want to say that was really impressive talk. It went fast and it was all very impressive.
Yeah, this was a
Right, yeah,
20-minute
that's the
talk
challenge
I
for-
gave yesterday. So that was a 20-minute talk I gave yesterday. So I had to shrink it to 10. That's why I had to go a little bit too fast. Sorry on that
30
side.
minutes.
Okay. Let's thank the student speakers once again.